Okay, let's find the equation of a tangent line to kind of a scary function here at the specific point 1, 1. So to do so, we're going to use implicit differentiation as we go. So let's jump right in. One term at a time here. Remember, if we have a y and take the derivative of the y term, or that part of the function, derivative of y with respect to x, we're going to put a y prime. All right, so the first term there, the negative 30x to the 9th power, use the power rule. We get negative 270 x to the 8th power. But our variable is x, so no y prime goes next to it. Now that middle term's a little bit tricky. And why I say that is, it's like we have both an x and a y involved there. So how I'm going to deal with this is I'm going to deal with it by treating that first part, the 8x to the 45th, as one function multiplied by a second function, which is just going to be the y. So if I write out the product rule in this case, for taking derivatives, it goes f prime times g, the derivative of the first part times the second, plus, keep the first part the same, take the derivative of the second part. All right, so derivative of 8x to the 45th, we're going to use the power rule. 45 comes down, multiplied by 8, 360. Reduce the exponent by 1, so we get to the 44th power. Next, we bring along the function I'm treating as g, which is y, plus copy down the first function, the 8x to the 45th, multiplied by the derivative of y is 1. But remember, y is the variable, right, that we're looking out for. So we took the derivative of y with respect to x, so next to that derivative we need to put a y prime. All right, the derivative of that last term on the left-hand side, power rule says 7y to the 6th power. But our variable again was the y that time, so I'm going to include a times y prime after it. All right, and then the derivative of the right-hand side, it's a constant, so its derivative is going to be 0. So you may notice I tried to highlight the y primes are what we're trying to solve for. Equivalently, we could have used Leibniz notation and said dy dx in each of those spots where y prime is. All right, the goal though is solve for y prime, get it on one side all by itself. So to do that, I'm going to go ahead and move the terms that don't have y primes to the other side. So I'm going to keep the 8x to the 45th times y prime on the left-hand side, and I'm going to keep the 7y to the 6th times y prime on the left-hand side. But the other pieces I'm going to move to the other side. So I'm going to add the 270 x to the 8th, and I'm going to subtract the 360 x to the 44th multiplied by y. Looks confusing, but I'm just moving terms from one side to the other side by adding or subtracting those terms. Okay, now I'm going to use the technique where on the left-hand side, both of those terms that remain have something in common. They both have a y prime. So what I'm going to do is factor out that y prime from each of those terms. What that's going to leave us on the inside of this set of parentheses is 8x to the 45th plus 7y to the 6th power. The right-hand side did not change in that step, so I'm just copying it back down. All right, all that remains is to actually get the y prime on one side by itself. So to do that, I'm going to go ahead and divide both sides by that big set of parentheses. All right, so that is the formula for our derivative. Now we're not quite done with this problem, but we're getting there. At this point in the semester, you should know that the derivative, y prime, means the same thing as the slope of the tangent line to the curve. All right, so our derivative is represented by that big fraction over on the right-hand side, but we care about this specific point over here at an x value of 1 and a y value of 1. So what I'm going to do is I'm going to replace each of the x's with 1 in this formula and each of the y's with 1 as well. So evaluating this, finding the slope of our line actually isn't that bad. It's going to be 270 times 1 to the 8th power minus 360 times 1 to the 44th power times 1, gets in there for that y, over 8 times 1 to the 45th power plus 7 times 1 to the 6th power, just plugging into that formula. Now, raising 1s to powers is actually pretty nice because 1 times 1 times 1 is always 1. So this works out to be 270 minus 360 over 8 plus 7. And we can reduce a little bit further. I think we have 270 minus 360 is going to be negative 90. 8 plus 7 is 15, which works out to be negative 6. Okay, so remember, we're looking for the equation of a tangent line. We now know the slope of our tangent line is negative 6, and we know a point on our tangent line, 1, 1, right? It's on the curve, but it's also on our tangent line. Let's put those two pieces of information together. So I'm going to use y equals mx plus b, the slope-intercept form of a line, and fill in here, right? So I have a y value of 1 from that ordered pair equals negative 6, the slope at the bottom, multiplied by 1 from that ordered pair, plus b. Well, that's really 1 equals negative 6 plus b. So to isolate the b, get it on one side by itself, we just need to add 6 to both sides. So we now know the slope, we know the y-intercept. Let's put those two pieces of information together and say y equals our slope, negative 6, times x, plus the y-intercept b. And that's the equation of our tangent line to this pretty scary looking function at the point 1, 1. So implicit differentiation takes a little bit of work to get comfortable with it, but it's not too bad. You just want to focus whenever you're taking a derivative of a y, you have to put a y prime next to it. All right, good luck.